we're going to make some general observations about finding the integral, the definite integral. The first observation is that we may select the sample point x sub I star to be any value that lives on the interval from x sub I minus 1 to x sub I. It could be a left endpoint, a right endpoint, a midpoint, or any value in between. If we choose to use the right endpoint, x sub I star equals x sub I, and then the definite integral in that case would be equal to the following limit equation. The limit formula for the integral using the right endpoint, x equals a to b of the function f of x dx is equal to the limit as n, the number of rectangles, approaches infinity of the sum I index equals 1 to n of f evaluated at the left endpoint the right endpoint x sub I times delta x, the width. If we, on the other hand, elect to use the left endpoint, then x sub I would be equal to x sub I minus 1. That's the left endpoint. And then the definite integral would be defined by the integral from x equals a to b of f of x dx is equal to the limit as a number of rectangles approaches infinity of the sum I equal 1 to the number of rectangles n of f evaluated at x sub I minus 1 times delta x. So you'll see, I'll pause this to say that the only difference between the right endpoint definition and the left endpoint definition for the definite integral is where you start f of x at. What x value do you start evaluating the function at? For the right endpoint, you start with x sub I, and for the left endpoint, you start with x sub I sub 1, I minus 1. Okay. Now, another thing we might choose to do is we may use any point that lives between x sub I minus 1 and x sub I, such as a midpoint, right? And so we choose any point to be our sample point. And usually we use the left endpoint or the right endpoint. And that's the two cases that we see in the cloud. Another comment I want to make in passing is that, by the way, we have defined the definite integral in note number 103 to be equal to a limit on continuous function f. And the fact is, it can be defined for something slightly different than a continuous function. If your function has, say, a finite number of removable discontinuities, we call those jump discontinuities in the past, a finite number of them, not too many of them. So if you have that type of discontinuity, a finite number of jump discontinuities, let me remind you what they look like here. Here's a graph. See how they just jump from one point up to a next open space and up like that? If you have a finite number of those discontinuities, you can still use that definition for the definite integral. But if you have an infinite discontinuity, you cannot use this definition. Example, if you have a function that does this, has an asymptote like this, an infinite discontinuity, you can't be using this definition from note 103. So in general, I want you to remember that note 103 is describing an integral that has values, a lower limit x equals a and an upper limit x equals b.